There we go. Find the magnitude of the moment of force F about axis BC. So this is different than what we've had so far. What we've had before asked us to find moment of a force about a point. Like, for example, moment of F about point B. That is a vector, and it's going to be R cross F, where R always starts from this point, goes to line of action of F. That's what we know. But this one doesn't say point B, point C, or whatever that point, middle point is. It tells us to find about this axis. It doesn't even say pipe BC, right? It's about the axis, which means anywhere on this axis. So now, what should I do to find moment of this force about an axis? There's another little tiny hint and difference in the problem statement that's asking you. Can you figure out what is that other minor difference in the problem statement? In that little sentence, find the magnitude of moment of F about axis BC.
It's only a magnitude?
Magnitude, yes. So this also tells us find a magnitude. It can very well say find a moment, right? Which could mean the vector, but right here it's only focusing on the magnitude. All right, so that's another kind of little detail. Let's go back to chapter 2 a little bit. I had a force F, and I had a line, right, random line, and the problem said find magnitude of F, right, along AA. Remember that? Or said find, instead of magnitude, it also said projection, right? Different ways of saying it. Do you guys remember what did we do? How did we find magnitude of F on this axis AA? What did I do?
We use the dot product.
Okay,
operator.
dot product of what?
Line AA and F.
So line AA, what about line A? Do you remember?
The unit vector.
Unit vector of it, exactly. So unit vector of that direction, or that axis, or that line, dot F. And vector dot vector equals a scalar. Makes sense. Magnitude of projection of F. So now in this chapter, what you got to do is exact same thing. Just change the letter F to letter M. That's it. You're going to do the exact same thing here. So magnitude of this moment along AA, or projection of M along AA. MAA, which is a scalar, going to be unit vector of AA dot M. That's it. Do you see the similarity? It's just the letter change and color of my pen has changed. And also, this is a vector dot another vector results in a scalar. So that's what we are going to do. But moment, we learn that it's R cross F. Okay. So this whole thing is going to turn into moment about, here is axis BC, for example, is going to be dot product of unit vector R cross F. So let's look back really quick. Unit vector of what? What is this unit vector of? Isn't it this same thing, same direction, same line, same axis? So unit vector of axis. Unit vector of axis, direction, line, whatever they're wording it, right? They can word it line BC or axis BC or line AA, whatever they call it, doesn't really matter. Unit vector of whatever we're trying to find a moment about, dot producted by R cross Fs. Sometimes if you look at the book, it might have a parentheses around it, doesn't really matter. Doesn't make any difference. All right. In the moment about a point, the R, the position vector, was from the point to line of action of F. So who can tell me what do you think this position vector is in this case? Because now we're not dealing with a point, so we can't say from point to F. So what is it from? Where is it from? Where is it to?
You're talking about B to C?
B to C. No. Because remember, unit vector of BC is pretty much position vector of BC divided by its magnitude. So it's like you're multiplying position vector twice by itself.
Anywhere on the axis of BC?
Okay, so again, this also is from axis BC to line of action of F. Okay, and I love how you said anywhere. To anywhere on a line of action of F. So here are some examples. Anywhere on the axis, I like to take it from here. Line of action of F goes that way down here. I like to take another one from axis to this line of action, R2. These are all acceptable. It is a little bit hard to understand it, imagine it, make the logic out of it, you know, in your head. How is that possible? Any point to any point, and it does not matter in my answer? No, it doesn't. You got to do the math. And that's the beauty of using this method, using the cross product and using the matrix. Because when you're changing the R, you're changing one row of the matrix, right? So all three numbers are changed. So that's why in your calculation, eventually all of those are going to cancel each other out. So you're going to get the same answer no matter what R you use. Just for fun of it, let's make another one. Axis. I like to go here also, R3. And anywhere, again, anywhere on the line of action to anywhere on the line of action, anywhere on the axis to anywhere on the line of action of the force. It's acceptable. Okay. But if you are smart, which you are, in this problem, which one would you pick? Which position vector would you pick to make your life easier?
I would go from B to A.
B to A, right? Because I have the coordinates. I'll go BA, or you can go CA. The important thing is you cannot go from A to C. I mean, you can, but you're going to get a flipped moment, right? It starts from your axis, or it starts from your point, it goes to the line of action of force, okay? Just be mindful of that. But yeah, you can take BA or BC, BA or CA, yeah. Okay, I made a huge mistake here and no one told me anything.
Yeah, it's your, it's because you put a vector over top of scalar quantity.
Exactly, this is a scalar. That was my big mistake. Oh, keep, what happened? There we go. Yes, this is a scalar. This is a scalar because dot product of two vectors is a scalar. And this is a vector dot another vector is going to be a scalar. Okay, so let me ask you this. Last lecture, I emphasized a lot and told you 10 times that moment of a force is always a vector. Moment of a force is always a vector. So how come I'm telling you now that this is a scalar?
Is that just a projected force on that axis?
Not force, moment, but yes, because this is a component of that moment on that axis, which, now I'm about to confuse you really here, which in the reality, this is also a vector because it has magnitude, right? Which is the one that I'm showing here, but also it has a direction, which I'm not showing here. Let's look back here. When I talked about projection of this force on this axis, right? FAA. What we find here is magnitude of this FAA, right? Magnitude of projection, magnitude of component. But that component is still pointing to somewhere. So it really has a direction to it too. But I'm not just showing it, I'm not finding that direction. So I'm just finding the magnitude of that moment about axis. In reality, it doesn't change the moment. Moment is always a vector, and I want you to remember that, and I want you to understand that, the difference. Just because we are finding magnitude of it, it doesn't change the moment into a scalar, right? So we are finding the magnitude of this by dot product. So I hope that is clear. So now let's get back to the problem, and now let's just start solving. Moment about BC as a scalar, because I'm just finding the magnitude, unit vector of BC dot product R, and doesn't matter. Let's go with BC, with BA, sorry. You can also do CA cross F. Okay, so I gotta find unit vector of BC. So unit vector of BC, coordinates are given, so it's going to be RBC divided by magnitude of BC. RBC is 0 minus 0, 4 minus 0, 0 minus 3. I, J, K. Divided by 0, 4, 3, which is going to be 5. So it's going to be 0.8 I minus 0.6 J. Doesn't have a unit. Okay. That's one thing I found. RBC, let's find it. Yeah, let's find it here. That's okay. I wanted to save some room, but it's going to be B minus A. I didn't draw the table anymore to just save a little bit of time, plus the coordinates is given right there. So it's going to be A. So it's going to be 4 minus 0, 2 minus 0, 2 minus 3. I, J, K. The units are meters. 4I, 2J, minus 1K units are meters. F, lucky for us, F is given minus 2I, 6J, 3K units are kilonewtons. Okay. Any questions about position vectors, unit vectors, anything like that? These are from chapter 2, but if you have any question, now it's time to ask it. Yes.
For the unit vector of BC, wouldn't the vectors be J and K, not I and J?
VC, they're both on, so it shouldn't have any
Because
I.
the I is 0.
Oh, yes, yes, you're right. Why did I put IJK? Yes, absolutely. Because they're on this plane, right? Both of them are on this. So unit vector of BC shouldn't have any X in it. So I don't know why I put yeah, this is J and this is K. Thank you. Okay. Any other questions or any other errors anywhere? Okay, so now we got a whole bunch of stuff, right? We have U, B, C, we have R, we have F. Let's figure out how should we use it? How should we do the dot product? Because we know how to do cross product. You know, you just put it in the matrix. Did I say BA before? BA, yes. BA, F. So let's just start with what we know, okay? We know if it was just R cross F, R would go in the middle, 4, 2, minus 1, and that should be M. And F would go on the third row, which is minus 2, 6, and 3. If I didn't have unit vector, I would put IJK on top, right? But now I can't because I have something else that needs to be factored in. Plus, putting IJK in this matrix is going to mess everything up. How? How is that going to mess everything up if I put IJK in the matrix? So the question is, if I put some sort of IJK anywhere in this matrix, how's that going to mess up my calculations?
You wouldn't get a magnitude.
I wouldn't get a magnitude because then IJK shows up somewhere, right? All I want out of this matrix, I should get a number. So everything that goes in it should be a number only. So now what do you think should go in the first row?
The unit vector.
The unit vector without the IJK, right? Do not put the IJK. 0, 0.8, minus 0.6, and has no units. So that's the only difference. When we are finding moment of a force about a point, you put IJK there, 4, 2, minus 1, and the force on the bottom, right? So let's just look back really quick here. We had R, X, Y, Z. We had Fx, Fy, Fz. This is for R cross F, right? So I put I and J and K on there. Can someone a little bit explain to me what IJK means when I put it in that matrix, now that you know unit vector of an axis goes up on top?
Wouldn't that put the answer in Cartesian form?
Okay, which means what? Let me help you a little bit. Let me put a 1 here.
Your quantity.
So this, what is this is, this first row is, aren't these X, Y, Z unit vectors?
I guess that gives the magnitude that you
So
have from R and F direction.
Exactly. So it gives you a magnet. So it gives you a moment, something I, something J, something K. This is a moment with 3 components about 3 axes. This is about X, right? This is about Y. This is about Z. You guys now see it? So even before on Wednesday, you didn't know you're doing this, but in Wednesday you were kind of sliding a unit vector into the matrix too, but it was disguised as IJK. What we actually do is we put unit vector of X, unit vector of Y, unit vector of Z in the matrix. Now now it's not about X, Y, Z. It's about an arbitrary axis, so we have to put unit vector of that axis on there. So I want to put these two next to each other so you kind of see these two are pretty much the same thing, but one gives you about X, about Y, about Z. One gives you just about any axis that you want, okay? Questions? You guys do the math on this one. It's just a simple determinant that you should be able to find.
Would it work if you did the cross product normally, just with the IJK and then dot product with unit
Yes,
vector?
absolutely, yeah. So the question is, what if I just did cross product first and then did IJK? The only thing is now you're dealing with an axis, right? when you want to do cross product, you got to be mindful of it, because the cross product that we have done, it was always about a point. So all you have to do is pick a point on that axis. But yes, you can basically do a two-step. Find moment of F about a point on the axis, which in this case would be about B, right? Step 2, dot product unit vector by that moment that you just found. This determinant is kind of a, you know, a shortcut to do those two. All right, here's one thing. I'm not going to give you the final answer, but your final answer is going to be negative.
Do you want us to say the answer out loud or?
Oh, sure, if you have it.
Negative 24.8.
Okay, I have it a little bit different, but close enough. So, what does that negative mean?
It's the direction.
Direction of what?
The moment of force about the axis. It's opposite of
Opposite
the
of?
rotation.
No, opposite of what? You were almost correct. Opposite of what?
Instead of going from B to C, it's C to B.
Exactly. This is opposite of your unit vector. Vector direction. Because our unit vector goes from B to C. It's a vector with a magnitude of 1, direction from B to C. I mean, the problem told us BC and we just put BC. We could have put CB. That's still correct. That's the same axis. So this only tells you, and that's why goes back that I said, hey, this is also a vector kind of disguised as a magnitude. Now you see why. This goes back to its direction. Although it's a scalar, but because moment is always a vector, it's really, really hard to get rid of the direction part of it. So the direction is always there. Sometimes we don't see it. If we got a 0.24, the direction is still there. You just don't see it. So although you find a scalar, because it's a moment quantity, is always a vector. Let's go back here.
Okay,
You see that?
Earlier you said you could pick any point, but I picked RCA and I got negative 24.8.
Okay.
To the math.
Which matches your own previous
Yeah.
calculation, right? Yeah, I
it
don't know
does.
why you got 0.8.
Well, because I'm just saying, because when I used like I said RCA, and that gave me 4 negative 2.2, and then when I did the cross product of then negative 2.63, I got negative 16 for the I value.
Okay.
The negative 16 times the dot times the I guess the dot product or the unit vector, that gives me then negative 12.8.
12.8 or 24.8? I can check it after the lecture for you for sure. See what you did. Okay. But if you do CA, you should get the same answer, at least the magnitude. Okay. If you do the BC, if you do the CB, this BC versus CB is the only thing controlling your direction, that is positive or negative. The BA or CA should give you the exact same answer. I've actually done it with CA2. I have the numbers for that too. The only thing that's changing if you do CA is going to be 4.22. And it gave me the same answer, 23.7. But I can definitely check your answer at the end.
Wait, why is it 4? Shouldn't it be 4 negative 2.2?
4 from CA, let's see. From C to A, 4 minus 2, and yes, so there we go. So 4 minus 2 minus 2. All right, any other questions? Okay, let's do another quick one. Okay, was there a question in the chat or? No? All right. So the steering wheel of the Ferrari I don't own, maybe someday. Is shown below. If I apply a force of this much to the wheel, as shown, what is the moment of this force about AB, which is a steering column axis, which actually steers the car? Okay. So let's read it again. Make sure we understand. The steering wheel of the Ferrari, blah, blah. If I apply a force of this much, as it's shown, to the wheel as shown, what is the moment of this force about AB, which is the steering column? So moment about AB. So it's going to be unit vector dot R cross F. I usually like to write this equation first and then go back and label it, right? So now let's look at it. Unit vector. What is that going to be? Unit vector of what?
AB.
AB, the axis, right? Whatever axis you're after, it's going to be there. Here we put AB or BA, doesn't matter. And then R is from what to what?
The line of action to the axis.
Opposite. It always starts from this, goes to the force. It always starts from the point or from the axis and goes to the force. So here we have A, we have B that are on the axis. I will pick A because I see that A is just 0, 0, 0. So let's take an easy one. A, C. And force F is given. Okay. Any questions? Is everyone following what we're doing and how we're labeling stuff? So the general rule is moment about axis is unit vector of axis, R, that is from axis to line of action of force, cross force. Because sometimes if you only look at the labeling and subscript, it's going to be confusing. All right, so now let's fill this, fill the matrix. U needs to go on top, first row. So let's find unit vector of axis. Unit vector of AB, I got to find position vector AB, divide by magnitude AB. All the coordinates are given. It's going to be minus 0.2 I, minus 0.5 K. I changed everything to meters again, which for unit vector really doesn't make a difference. Okay, it's going to be minus 0.97, and it's just I and K, yes. J is going to be 0, K is going to be minus 24. No units. Okay. And position vector AC, this one I turned everything into meters. So I did it by meters. It's going to be 0.1 I J minus K 0 K meters. So I'm going to put 0, 1, 19, 0. And F is given somewhere, it's up there, minus 12, 0, minus 3, and that is newtons. Okay. So let's see, can someone do this? Do the math? Well, by someone, I mean all of you should be doing this.
Negative 0.0057 Newton meters.
Exactly. And if you do millimeters, you're going to get a little bit larger number. Well, the same number, but just less decimal points. But yes, it's going to be minus, which again, the minus is just goes back to the axis, Newton meters. So now, my question is, why is this so small? Does that make sense to you? I told you, like every time you find an answer, and if it just your calculator shows it, that might not be the correct answer. You got to think about it, right? So now let's go back and look at the figure. Look, what is this? And these are real numbers, so it's not made up. So it's like, oh, maybe we should have put a different force. No, this is actual force, and this is a real situation. Why is it so little? How does that make sense?
Because if you're steering a car that has power steering, it doesn't take much force to turn the wheel.
Not really.
Is it because you're basing your steering off of meters and you're not moving your arm a whole meter trying to turn the steering wheel?
Still no. Maybe well, you know, I got to rethink it. But no one has told me what I'm looking for still. So let's think about it. If you're driving and you're putting that force, you got to kind of look at the axis and kind of think about it, which way the force is pointing. And you have this much moment. How is that affecting your driving? Because here's the deal. This moment is almost zero. Pretty much zero moment. So how does that make sense? And I mean, once I tell you the answer, you're going to laugh, but it's not a trick question, but I just want you to think about it. Why did I get such a low number? What is happening with this person?
Because there's not a lot of force going into the steering column.
Yes, which happened, which
in a straight line.
Yes, that's what I was looking for. This person is just going straight. It's not creating a moment to steer the car pretty much. That's pretty much what I was asking for. Yes, it makes sense. This is a low, small number because if I think about the force is going mostly in the X direction, right? So the person is just kind of holding it and pushing it forward a little bit with a little bit downward also, right? And it's just going straight. It's tilting the car a little bit, but it's not steering it, right? Or creating any tendency for rotation, because this is pretty much zero, which depending on what you use, a lot of students in the exam, they said they got zero, which was also a correct answer, depending on how much you round off and stuff. So just pay attention to numbers that you get. Does it make sense? Go back and think about the force, what is happening, what is the result of this and stuff like that, okay? Question, believe it or not, this has been an exam problem a couple of times. So I mean, if you know what you're doing, this problem like this takes only a couple of minutes. Questions? Okay, so let's do another one. A little bit more work. I shouldn't say complicated. Okay, force F of this much is applied to the tool as shown. Find the magnitude of the moment of this force about the x-axis. All right. So let's first of all write the equation, right? It's always a start with the, which they call governing equation. So write a governing equation. Moment about x-axis equals unit vector dot product R cross F. Everybody follows me so far? Unit vector dot product R cross F. Now let's go label it. What is that U supposed to be? Unit vector of what?
The x-axis.
The x-axis, right? Whatever axis you have here, BC, BA, in this case x, you have to just do unit vector of x-axis. Okay? What is the R from, and where is it going to?
O to A.
So it goes from x-axis, right? From axis to line of action, which in this case, it's better to take O to A. I agree. And F is your force. So you got to find a couple of things. Unit vector of x-axis is easy. What is unit vector of x-axis? So what goes on the top row?
1. 1I and then divided by 1.
1 divided by 1, just 1, 0, 0. Does everyone agree with that? Unit vector of x-axis. That's actually what we define as I, right? Unit vector of x-axis is just I. That's definition of unit vector I, Cartesian unit vector. Or if you want to be too accurate, it's 1I plus 0j plus 0k. All right. OA, do we have point A? So position vector OA, point A is located at 0, 0. Y-axis is 0.3 right here, and Z-axis is 0.25. So 0 minus that, 0 minus that, or sorry, 0 minus 0, 0I, 0.3 minus 0, J, 0.25 minus 0, K, and those are all meters. So let's put it right in the matrix right away. 0, 0.3, 0.25. And these are all meters. This has no units. Now force F. That's where it gets a little bit, got to work for it. Force F, I have, the only thing I have is magnitude of it.
Well, you have all the angles, so
I have the angles, which are called what?
alpha, beta, gamma.
Coordinate direction angles.
Coordinate direction angles, alpha, beta, gamma. So let's figure out, before putting them into equation, make sure that they're, first of all, they're all with positive axis, and figure out which one is alpha, which one is beta, which one is gamma. 20, this is alpha, right? Yes. With Y, this is beta. And with Z, this is gamma. And to me, they're all with the positive axis. And one other thing to kind of pay attention here, do you see like it's not going literally to Z axis, right? Because all we care about is the direction. So that's why you just put a thinner line right there and just finding the angle with that, which is the same if it goes all the way to X axis. It's just the direction that matters, okay? So let's see, once we know that, it's pretty easy. 200 newtons, cosine alpha I, cosine beta J, cosine gamma K, right? That's from coordinate direction angles. Coordinate direction angles. So now, when you guys look back at chapter 2, all you had to do is like find, for example, this F. Remember some of the problems? Now those problems seems very easy. Problem just gave you a F angle, said find this. Once you did that, you were done. But now you can see that's just a small portion of your solution here. So if you do that, you're going to get minus 100, 100, 141.4. Okay. You guys do the math again on your own. I want you to get practice doing the matrix so you can do, which in this case is just 1, right? Get rid of this, get rid of that. 0.3, 0.25, 100, 141.4.
17.42.
Well, you ruined it for everyone else. I'm just kidding. This, I mean, it's always appreciated. But yes, please do the math and get practice. Yes. Was there a question? Sorry.
With the exams again, if we like show you how to get to this step, can we just use our calculator to solve the matrix?
Yes, yes. Good question. So exams, this is what I will be looking at, I'll be grading you at, okay? And then if you just tell me that it's 17.4, that's fine. Okay, that's totally fine. One thing that I've seen with these problems, the biggest problem students have is they put IJK in here. They kind of ruin the answer, and it's wrong. Okay, because we talked about it. We want this to be a vector. Sorry, we want this to be a number, a scalar. So that's why we do not include IJK.
Or
Right?
if they did it in 2 steps, though, that would technically still be right, because then they're
Yes.
vector and then doing the dot product of 2 vectors.
Yes. So if they, actually, you know, I'm glad you mentioned. In my solution that I did for myself, I did a 2-step for this problem to explain that, hey, you can find it about origin. So if you do moment about O, right, R cross F, that is totally acceptable, which is going to be OA cross F. You get a something I, something J, something K, and then all you have to do is just pick the I component, and that will be correct. But if you are doing a U dot R cross F, do not put IJK in your matrix. Okay. Questions. These are actually my favorite problems because they're very, very straightforward, very easy. All of them starts with this. Okay. All of them starts with this, and you just got to figure out the labeling it. And the labeling it, the way I did it today, and in my lecture videos, this way, it doesn't hurt to make that arrow for yourself or write access there. It just prevents confusion and prevents little error mistakes, labeling stuff like that here and there. Okay, so always have that equation on that corner, have those arrows that I put on there, have the labels, and you guys should be fine for all the problems that asking for about an axis. So one last thing, we have like 2 minutes. Why do we care to find moment about an axis? Why should we bother to find a moment about an axis? And this problem is actually a great example for that. Again, if you watched my lecture videos or read the textbook, I go over this, but let's talk about it. Why should I bother to find moment about an axis? How is that going to help me with anything?
Somebody in class said because of torque.
So that's exactly what it is. Like this problem that you see, this person is applying some force that's going kind of in space, right? But you want to know how much of that force is actually used to turn that bolt at point A, or how much this force is causing, as someone said, a torque, which in this case would be correct because it's on a shaft, it's on a bolt about point O. So that's the reason we do that. If you look at the book figures and some of the figures I use my video lectures, there's a lot of examples of changing a tire on your car. You know, you might put different forces in different directions, but all that matters is how much of that is actually going to loosen that bolt on your car tire. So that's why we care about it, and sometimes we need to find that that component of that moment. Okay. Questions? If there's no questions, you guys are good to go. Don't forget about activity 4 if you haven't done it. And cheer for Bison this weekend. All right, so I can check your
I have a quick question.
Answer. Sure, yes.
So when we're finding this moment, like about an axis, like point or the axis X per se, just be like an instantaneous, like as soon as you start moving it, wouldn't the axis change? So is that force only for that instantaneous, like little movement, like right when we find that?
Yes. So, you know, again, we are dealing with the statics, right? So our assumption that is nothing is moving yet. So by putting that force, you are putting this much moment at point O
Yeah.
in this direction. No, it's before everything moves, because you're right. As soon as you move it and the force moves, the moment is moved, and that's a continuous, or as you said, instantaneous change in moment. But we're looking at it because, again, this course is statics. We're looking at it at that moment in time when everything is perfectly standing still. But yes, you're absolutely right.
Okay, that makes a lot of sense. I was just kind of curious.
Yes.
Thank you. Have a good weekend.
Yes, you too. Thank you. Any other questions?
Yeah, I just want to see, can you go back to that problem? I want to see if I maybe wrote down the wrong negative.
Yes.
I know
Yes.
that this math that I did is 100% correct.
Yes, let's do it. So I'm gonna stop the recording now. Well, we'll